All right, so now let's go ahead and look at the second day notes, which is graphing these logarithmic functions. And it's not a hard concept, but there's some important things you want to know. One, we know this is an exponential function. And a lot of times when we graph them, we would usually go with a table of values. Okay? If we look at a logarithmic function, here's what you have. Y equals log base a of x. Now, when I graph this, what I actually do is I write it in exponential form by saying my base a to the y power is equal to x. Now, x and y are still going to be my variables, but it's much easier to create a table of values from that exponential form. So when we look at this, right, remember we talked about in the last chapter that, the exponential form and the log form are just inverses of each other, as you see here. So when you look at, if a is between 0 and 1, if you look, this is your exponential form because it's kind of like decay. All right, but when we look at the logarithmic form, right, it's the inverse of it. All the ordered pairs are just reversed. Here we have exponential growth because a is greater than 1. And if you take the inverse or flip all the ordered pairs and graph them, you would get the logarithmic function. So some people would even graph the exponential function and just find the inverse by flipping the x and y coordinate in the for the ordered pairs in the exponential graph. Now, if you look here, the one thing about these logarithmic functions that I want you to know, there are three very important points that always occur. One ordered pair is 1, 0. Okay? Now, when these are transformed, that might move, but in the base form, in a way, in the standard form, log base a of x, 1, 0 is always a point. Then a comma 1 is always a point. And then a third point is always 1 over a comma negative 1. These are three easy points that we can always gather right away. So let's take a look at how to graph this. We're going to do it the two ways. First way we're going to do it is create the table of values. If I go to create the table of values, right, I have x, I have y. What I'm going to do is rewrite this in exponential form. My base of 2 to the y power equals x. Now, if you look, back in the day, we used to go ahead and input x values and get output y values. Well, in this scenario, when we go to create the table of values, it's easier to input the y values and find the x values. So if I pick y values of negative 1, 0, 1, 2, and even 3, now, what is 2 to the negative 1 going to give me? It's going to give me 1/2. So now, when I go to graph this, 1/2, negative 1, we're right about here. Okay, if I plug 0 in, 2 to the 0 power is equal to 1. So when y is 0, x is 1. So I'm going to plot that ordered pair. Then when y is 1, 2 to the first power is 2. So x is 2. When y is 2, 2 squared is 4. Now, when I plot these, I have 2, 1, and I have 4, 2. And this is what our graph would look like. Now, the one thing I want to bring to your attention is there's this whole idea and concept that when this graph is actually continuing, it's going to continue down here. It's get real close to the y-axis, but it's never going to cross. What we say is this y-axis is going to act as a vertical asymptote, right? And this is what the graph of your logarithmic function would look like. Now, the only other way to graph this, right, real quickly, is to know those 3 points we talked about. We know 1, 0 will always be a point. So plot 1, 0, and then you know A, comma 1 is always a point. So what is A? A is 2. So you know 2, 1 is a point. And then you would find your third point. Okay? But that's another easy way to do it, is to know that these 2 points will always be a point on the graph. So let's actually talk about, when you look at the domain of these, the domain of this is basically going to go from, it's going to be a round bracket on 0 and go to positive infinity, right? And the reason is, if you think about it, can you raise 2 to some power and ever get a negative number? No. So the domain goes from 0 to infinity, and my range actually would end up being all real numbers. So negative infinity to infinity. Okay? Now this one, right, is a little more complicated because of the fraction. So if we go to graph it, we're going to say 1/3 to the y power is equal to x. That's just taking this log form and rewriting it in exponential form. So 1/3 to the y is equal to x. So now if I make my table of values, x, y, I'm going to pick y values, and I'm actually going to go say -3, -2, -1, 0, and 1. And the only reason is because it's a fraction. You'll see why in a minute. Now, if I take 1/3 and I raise it to the -3 power, what you have to understand is 1/3 to the -3 is, I'm going to take the reciprocal of 1/3, which is 3, and I'm going to raise it to the +3 power. So this actually ends up being the same as 3 to the 3rd, which is 27. And again, if you do this on the calculator, put the fraction in parentheses and just evaluate it there. The next one, 1/3 to the -2 power, is the same as reciprocal of 1/3 is 3. Make the exponent positive, which is 2, and you get 9. 1/3 to the -1 power is 3 to the 1st power, which is 3. 1/3 to the 0 power is 1. And 1/3 to the 1st power is 1/3. So now, if we go to plot these points, 27 is going to go off the graph, no biggie. But 9, -2, 3, -1, 1, 0, and then 1/3, 1. If you look here, your asymptote for this still ends up being the y-axis, but if you remember, exponential decay starts high and gets low, right? This is the inverse of that, okay? So when we look at our properties of logarithmic functions, right? Log base a of x. So we're not doing any transformations, we're not adding, subtracting, doing anything to it. But here, the domain is always going to be from 0 to infinity. That's your base start. All right. Now the range is a set of all real numbers, because you can go all the way down to any negative y value and all the way up to any positive y value. The x-intercept is always going to be at 1, but we notate this as an ordered pair. And the x-intercept is actually always going to be 1, 0. In this standard form, there is no y-intercept. The y-axis, all right, x equals 0, is a vertical asymptote, which a graph will never cross. It's decreasing when a is between 0 and 1, and increasing if a is greater than 1. So remember, this is like a is greater than 0 and less than 1. It's going to be the inverse of exponential decay, whereas a greater than 1 would be the inverse of exponential growth. These are your 3 standard points that you can always start with by graphing. And then the graph is smooth and continuous with no corners or gaps. that should be pretty common sense here. Now, the one thing the video didn't talk about, or any of the videos yet, is generally we see, like when we have logs, we'll see y equals log base something of x, right? Well, here's the thing. If you just see, and on the calculator, there's a button for it. If you just see log, right? What that means, if I see y equals log of x, and they don't show you a base, that is no different of being y equals log base 10 of x. So if you just see log of x, that is the same as log base 10 of x. Okay? Now transformations. If I go to my calculator and graph the parent function y equals log of x. So when I do y equals log of x, right, basically it's base 10 right now. And if I graph that, that's what I get. Okay? Now, what happens if I go ahead and I graph y equals log base 10 basically of x plus 2? What's going to happen to the graph? So log of x plus 2. What do you see happened here? Well, if I just look at the ordered pair 1, 0, it went from 1, 0 to negative 1, 0. So what happened to the graph? It actually shifted, right? It actually shifted 2 units to the left. So when we go to talk about this, anytime you add something in here, right, that's going to shift the graph left. Okay? So what do you think is going to happen when we subtract 1 inside? So if I go to the same thing and I compare it to the parent function, and I go x minus 1, and I hit graph, now which way did the graph move? It shifted from 1, 0 to 2, 0, so it went right 1 unit. Shifted right 1 unit. Now, if we add something outside the log, so anytime you look at this, you evaluate your log, and then you're going to go ahead and add 3. What happens when we do this on the calculator? Well, y equals, I'm going to go log base x, close parentheses, plus 3. And when I graph it, now look what happens, right? You went from 1, 0 to 1, 3. Therefore, it shifted the graph up. It went up 3 units. So what do you think is going to happen if I subtract 2 on the outside? That means it's going to go down 2 units. Okay? And if I show you that, y equals, and I go down, and I subtract 2, and it's tough to see on here because I don't have the window there, but it was shifted down 2. Now, when I look at the next one, right, negative log x. What happens here when we take, I'm just going to clear this out, and I'm going to go negative log x. What happens here? They end up being, if I look at it, they end up being a reflection of each other, all right, over the horizontal line. So what this does is it basically reflects. And if I go 5 log x, right, if I go y equals and I go 5 log x, it definitely just kind of grew in a way, right? So we won't use this one a lot, but you have to be aware of it. But I would just take your normal table of values and multiply all the y coordinates by 5. Okay? So looking at the example 3, if we had to graph this, okay, if I had to graph this, the first thing I would do is graph the parent function real quick because it's easy. And I'm basically graphing 2 to the y is equal to x. So I have my x values, my y values, and again, I'm just going to plug in the easy ordered pairs, 1, 2. So 2 to the negative 1 is 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. So what I'm going to do is graph this parent function. 1, 0, 2, 1, and then 4, 2. Now if I went to 9, 3, that would be fine, doesn't matter. This is kind of what the parent function would look like. So now the easiest way to graph this is, what did we say subtracting inside the quantity does? When we subtracted inside the quantity, it went right 1 unit. So what I'm going to do is use this parent function, and I'm going to move each point 3 units to the right because I'm subtracting. It goes 3 units to the right. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And now this would be the graph of y equals log base 2 of x minus 3. Okay? Next one. First thing I'm going to do is I'm going to go ahead and graph the parent function, which is log base 10 of x. So 10 to the y equals x. So when I look here, right, I'm going to let y equal 0, and then I'm going to go 1, and then 2. So 0, when y is 0, 10 to the 0 power is 1. When y is 1, 10 to the first power is 10. When y is 2, 10 to the second is 100. So now I'm only going to actually plot the 2 points, 1, 0, and then I'm going to go 10, and then 1. So this is kind of what this will look like, right? Now, it is going to continue down here, and your asymptote is still going to be the y-axis. So here, when I look at this, this 2 makes it a little more difficult. What I know is I'm going to already add, right, to the... So right away, if I go to graph this function now, right, I know I have this ordered pair. I have 1, 0, and I have 10, 1. Now I do have 102, okay? And if I did go to negative 1, right, I would be at 1/10, which is not the easiest to graph because 1/10 is so close to 0. Now, looking at this, anytime we have this, so these are the ordered pairs for the parent function. So now, what can we do to get our new ordered pairs? Well, the only value that's truly changing in this is our y value. So we know these x values are going to stay the same. So it's going to be 1 and it's going to be 10, right? And the reason the y value is moving is because we're adding 5, but what are we doing to this value first, right? Well, I'm first multiplying it by 2, and then I'm adding 5. So right away, when I look at 1, 0, that ordered pair is going to go to 1. Then I'm going to go 2 times the 0 plus 5 would give me 1, 5. Over here, this would be a 10, 1. So now I'm going to do 10, and then comma, I'm going to take 2, multiply it by 1. That's the y coordinate here. And then I'm going to add 5, which puts me at 7. If I did do it for this ordered pair down here, it'd be 100. Comma, 2 times 2, which is the y coordinate, plus 5, which gives me 9. So in this case, I'm going to go from 1, 0 to 1, 5. I'm going to go from 10, 1 to 10, and up to 7. Oh, right here. And my asymptote still stays the same, and that's what it would become. Okay, so remember, you're doing 2 times the y value and then adding that constant on the outside. All right, next one. I'm going to plot the parent function, and I'm just going to do my 3 quick ordered pairs and maybe one more. So 3 to the y equals x. So right away when I go to make these ordered pairs, right, we're going to have if y is 0, x is 1. 3 to the 0 power is 1. When y is 1, right, 3 to the first power is 3. Let's go ahead and do one more. When y is 2, x is 9. So I'm going to plot this parent function quickly. So you have 1, 0, 3, 1, and then you have 9, 2. So right now, this is your parent function, and that's pretty ugly. Let me try and fix that. So you have it come down here, and then that's a little better. So now if I look, I know this tells me I'm going to go left 1. This tells me I'm going to go down 2. So I'm going to go to each ordered pair here. I'm going to go left 1, down 2. Then I'm going to go left 1, down 2. Left 1, down 2. And now I can graph that function. Okay? But now what I want you to notice is if my vertical asymptote, if that vertical asymptote was at the y-axis, right? So x equals 0. If you think about it, if this whole function shifted left 1, if all these ordered pairs went left 1, what do you think is going to happen to the asymptotes? It's going to shift 1 also. So your vertical asymptote here would be at the ordered pair x, or the equation x equals 1. It'd be that vertical line there. Okay, so go ahead, try the homework, and let me know if you have